Dear learners, I am Dr. Venkatakrishnan, Assistant Professor, Department of Mathematics. In this video, we'll be discussing the correlation of two random variables. So already we know what we mean by a random variable, two-dimensional random variable. That is, we repeat a random experiment in identical situation for n number of times, and on that we define two random variables x and y. The ordered pair xi comma yi is called the two-dimensional random variable, where xi is the values of x corresponding to the ith trial and yi is the value of y corresponding to the ith trial. Now this correlation is the process of studying the degree of relation and nature of relation between x and y. The difference between nature of relation is if x increases, whether they are directly related or inversely related. Degree of relation is how far they are related, and these things we can get from the correlation coefficient. So correlation is nothing but determining the nature of relation and degree of relation. Now we shall take the Karl Pearson's coefficient of correlation. The formula to get this Karl Pearson's, the notation is Rxy. And we also have the rank correlation where they use the notation rho xy. So this is Karl Pearson's, the notation Rxy. It is given by covariance of x comma y divided by sigma x into sigma y, where sigma x is the standard deviation of the random variable x and sigma y is the standard deviation of the random variable y, and standard deviation, as we all know, it's nothing but the square root of the variance. And we last video we discussed covariance and variance. So variance is nothing but the how far a random variable deviates from its mean, that is sigma x squared minus sigma x the whole squared. This gives the variance by n, of course the average value. Hope you remember. If you want, let me also recall here. So here we know the formula to get covariance. So formula to get the covariance of x comma y is expectation of xy minus expectation of x into expectation of y. Equivalently, you all know it is nothing but the arithmetic mean. So it is xi into yi divided by total number of values minus sigma xi by total number of values sigma yi by total number of values. It is the arithmetic mean of the random variable x. If it is if you have the numerical values, if the probability is associated with it, it will be the weighted average that we have discussed earlier in our earlier lectures. And now the variance of x, that is sigma x square of the standard deviation, it is nothing but e of x squared minus e of x the whole square. So e of x squared means it is if the values of x are known, just tabulated, then e of x squared is nothing but the arithmetic mean of x squared minus e of x means arithmetic mean of x. And you all know if the probability distribution of x is given, we have to go for the weighted average. Similarly, sigma y square is not going to be sigma y square by n, the arithmetic mean of y squared, and sigma e of y is arithmetic mean of y, sigma y by n. And these various representations we have given in the next slide. So if we go for the simplification, that is we are just substituting the formula for covariance and variance, and this could be further simplified as we discussed in the previous slide. And this formula we can use when the probability distribution or probability density of x and y are known. Instead, if we are listed the values of x and y without their probability, then we can use this formula. And this could be even further simplified by taking the LCM. For example, here In the second term, we have 1 by n squared as our LCM, right? So here in the numerator, n squared will be our LCM. So 1 by n squared into n into sigma xi yi minus sigma xi into sigma yi divided by, in denominator also you can pick n squared as LCM. From this factor we get 1 n squared, from this factor we get another n squared. So when pulled outside the square root, we have 1 by n into 1 by n, that is 1 by n squared root of, here we have only n, so we have to multiply this by n into sigma xi squared minus sigma xi the whole squared into root of n into sigma yi squared minus sigma yi the whole square. However, we have listed this formula in the next slide. So that is what we have done here. We have taken the LCM and simplified. So we have got the same result as we discussed in the previous slide. So if the values of the random variables are listed instead of the probability distribution or probability density, this formula we can use. So number of n stands for the number of values, and the xi, the I x values when the trial is repeated I times, and y will be the outcome of y at the ith trial, the value of y at the ith trial, and this is nothing but square of those values. Okay, now we shall discuss the properties of correlation. Any correlation coefficient, Karl Pearson's correlation of coefficient lies between -1 and +1, and based on these values we can say how we can express how good the variables are related. For example, when it is positive, it gives the nature of the relation, that is they are directly related. As x increases, y will also increase. That type of relation we call as direct relation. So in those cases the correlation coefficient will be positive. Whereas if the correlation coefficient is negative, that is if it lies between -1 and 0, then they are inversely related. As one variable increases, the other variable will decrease. Now how well they are related, that we can decide based on the specific value of Rxy. There we discuss the general positive negative case. Now if the correlation coefficient lies between -1 and -0.5 or 0.5 and 1, then we say the variables are strongly related. If you plot the scatter diagram, the points will be very dense along a particular curve or a straight line. Mostly the Karl Pearson's is, we call this as a linear coefficient of correlation. So they will be aligned along a straight line. Okay, all the points of x and y, x comma y, will be very close to a straight line. But when they lie between -5 and +5, then they will be bit scattered away. More number of points will be scattered away from a straight line that will pass through many points. Okay, right. Now this is one important property that will help us in handling the data, big data. If the values are bigger, we can go for change of scale, that is we can subtract by a particular value, that is shift of origin. In case of change of scale, we can multiply by some value, that is if 10 is, all the numbers are multiple of 10, then we can divide by 10, that will reduce our data. So value of the data. So whenever the data we are discussing with are very big numbers, we can go for shift of origin initially. If there is any common multiple, we can also go for a change of scale. So that will help us to deal with smaller numbers comparatively. And now if the two random variables are independent, then they are uncorrelated and their coefficient will be 0. But the converse need not be true. Suppose the correlation coefficient is 0, then the two random variables need not be independent. This we discussed even in the covariance case. When the two random variables are independent, their covariance is going to be 0, because we know E of xy is equal to E of x into E of y when x and y are independent. But covariance 0 need not imply the random variables are independent. Now let's have the first problem. Here we have the values of x and y listed here. So you know the formula involves x squared. X squared is obviously going to be a 4-digit number. 8 times a 4-digit number, we may get 5 or 6 digits. So that is difficult to deal with. So we can go for a change of shift of origin initially. This you can choose any value. Here I have chosen 67 for x and 68 for y, but the choice is ours. We can go for any value, shift the origin by any value. The final result is going to be the same, because the correlation coefficient is independent of shift of origin. So now I have tabulated vertically the values of x and y. Now I initially compute the value of u, that is from each x value I subtract 67 just to make it simple. So we have 65 minus 67. Here we have x minus 67. So 65 minus 67 minus 2, 67 minus 67 0, 66 minus 67 minus 1, 71 minus 67 4, and so on. And then now we find the V column, where we multiply each, we subtract 68 from each of the y value. So 67 minus 68, 68 minus 68, likewise we compute for all other values. Now in the formula for correlation coefficient, we need u squared, v squared and uv. So we have also computed those columns and we have got the total. So the last row is nothing but the total. So here we have got the summation of these values that will help us to directly substitute in the correlation coefficient, formula for correlation coefficient. And we know we have discussed in the properties that correlation coefficient is independent of shift of origin. So Rxy is going to be same as Ruv, and just apply in the formula. Here n is a number of data given to us. So here I think we are given 1, 2, 3, 4, 5, 6, 7, 8 data is given. So n is equal to 8. Sigma ui vi, that is the sum of the uv column. Take the ev column, the grand total, it is sigma ui vi. Sigma ui, take the u column, the grand total 7, it is sigma ui. Similarly, sigma vi is the grand total of the v column. Sigma u square, the grand total of u square column. Sigma v square, grand total of the v square column. And these substitutions we make in the formula. So we have 8 into sigma ui vi, that is 15. Minus sigma ui is 7. Sigma vi is 2. And then n into, that is 8 into sigma u squared, that is 35. Sigma u, that is 7 squared. And then again n is 8 into sigma v squared, it is 42. Minus sigma v the whole square, that is 2 squared, and finally the answer is 0.3828. Now we shall discuss one more problem given the joint density function of the random variable. So we are given that the joint density is f of x comma y is x plus y, and the region is 0 to 1, 0 to 1. So here if we plot the region, because it will be very useful while computing the marginal densities. We need the marginal densities to get expectation of x and expectation of y squared, and expectation of y and expectation of y squared. Now we are given that x varies from 0 to 1, the y axis is x equal to 0 and x equal to 1 we have here. Similarly, y equal to 0 is the x axis and y equal to 1 will be here. So this is our required region. This is the domain of the joint density function. Now let us first compute the expectation of xy. So it is given by the formula integral minus infinity to infinity minus infinity to infinity xy into f of x comma y dx dy. So here the limits are going to be the domain where the joint density is defined. Here it is a square region. So we have the limits to be 0 to 1, 0 to 1. And upon evaluating this double integral, we get E of xy is equal to 1 by 3. Now let us compute the marginal density of x. So marginal density of x is nothing but integrate the joint density with respect to y in the domain. And here we have the domain to be the square region. So no doubt it is going to be 0 to 1. So if you want the limits of y, we have to take the vertical strip, and here we know y equal to 0, here it is y equal to 1. So we have 0 to 1 the joint density x plus y dy, and on evaluating we get x plus 1 by 2. And similarly the marginal density of y, we have to integrate with respect to x. So to get the limit of x along the cover the region using the horizontal strips, and the strip starts at x equal to 0 and ends at x equal to 1. So the limit is 0 to 1, and on evaluating the integral we get the marginal density of y to be y plus 1 by 2, and then we go for the expectation of x. It is nothing but x into marginal density of x. We got the marginal density to be x plus 1 by 2, just now we have evaluated. So the marginal density is x plus 1 by 2. So it is x into marginal density, and on evaluating the integral we get 7 by 12. Next we go for the expectation of y. It is y into the marginal density of y, that is y plus 1 by 2, and then evaluating we get 7 by 12. And now we go for the expectation of x squared, because in the formula to get the variance we need sigma x squared minus sigma e of x the whole squared. So if we want the expectation of x squared, it is x squared into the marginal density of x. So it is x plus 1 by 2, and in the domain x ranges from 0 to 1. So upon evaluating the integral we get 5 by 12. Similarly next we go for the expectation of y squared, which is nothing but again it works out to be 5 by 12, and now we substitute in the formula for Karl Pearson's coefficient of correlation. It is expectation of xy minus expectation of x into expectation of y divided by root of variance of x, that is expectation of x squared minus expectation of x the whole squared, and variance of y, expectation of y squared minus expectation of y the whole squared, and just substitute the values we have evaluated so far, and finally we get minus 1 by 11. And same way we can proceed in the case of two-dimensional discrete random variables when we are given the joint distribution function. And with this let's wind up this video, and in the next video we'll be discussing the regression, equations of regression. Thank you.